This talk is about the maps, the brain maps that you get from machine learning. And a part of the talk is on the spatial regularizations, which is kind of the answer we're posing to a problem. But part of the talk, I'd like it to be more general and to be more food for thought about the problem itself. So, brain mapping historically is really about detecting voxels that correlate to a given stimuli. So that's really the standard brain mapping framework that's being used everywhere. And it's really mass univariate, which means that you're doing one statistical test per voxel. So you have a really good idea of what you're testing per voxel. You have a null hypothesis, you know what you're doing, and what is one of the limiting things of this approach is that it is killed. The statistical power is destroyed by multiple comparisons. Also the fact that it's univariate, but maybe that's not a problem given that it means you know what you're doing. On the other hand, so there's the decoding approach, which in fMRI would be predicting some description of the stimuli or the cognitive state, and it could be for clinical applications as we've just seen. And so this is really what we call a supervised learning task. So it's a learning problem, and intuitively the idea is that you're going to find a combination of voxel values that predict ideally. So now the problem as it's formulated is fairly different than the brain mapping problem. So the thing is, if you look at the papers, quite often part of the take-home messages talk about the brain regions and not only about the prediction. And that's over and over and over again, including in papers like clinical applications where you would expect that only the prediction matters. And the reason is behind this that we'd like to go from prediction to prescription, which forces us to at least have an understanding of what is used to predict. So that's really a core problem. It's been in many of the talks that we've seen so far. So one application that I like of decoding is about cognitive neuroimaging, and here's a little slide on philosophy of cognitive neuroimaging. So brain mapping is naturally telling us what is the neural support of a given function if you design your experiment well enough. Some people would like to ask the following question: what is the function of a given brain module? And now if you think about it, that's the exact reverse question than what brain mapping is telling us, right? So the function of a given brain mapping is a reverse inference compared to what brain mapping is giving us, because brain mapping is just giving us which voxels are recruited by a region, right? So this has been put forward quite strongly by Russ Poldrack in a TICS paper a few years ago. And so then you get in all kind of debates like, is there a face area, yes or no? Well, it's a bit hard to actually reply to this question by just asking what are the neural correlates of faces. So in this sense, decoding can provide an interesting answer, which is to find regions that predict the observed cognition. It's just one use of decoding. It's decoding for reverse inference. But that's one that I use often, and it's one use that is telling us why it might be important to find the predictive support of the decoder, right? And so even in full brain. So that was a small philosophy of science slide of why sometimes it's useful to look at brain maps. Now I'm going to tell you why it's dangerous to look at brain maps when you're using decoders. That will be my first part. Then I'll try to open a bit the black box and to have an idea of why decoder work and what they may do to brain maps. And then finally, I'll provide one answer, which is spatial regularization, and hopefully I'll convince you why I think it's a good and important answer. Okay, so let's look at a trivial historical example, which is face versus house visual object recognition. You're looking at visual activity, and you're trying to predict whether a subject is seeing faces or houses. So we can apply an SVM on this, which is maybe the most standard decoder, and we can apply this on a mask of the ventral temporal cortex, and we get an error of 26%. Now we can apply a sparse model, a sparse logistic here, and we get a smaller error, and the brain map is significantly different. So we can discuss whether we like it or not, but it's very different. And we can apply a ridge regression, which is another decoder, and we get yet another brain map which with an even smaller error. Okay, so which one is the correct brain map? If we believe in prediction error, it's the last one. But if it looks a bit, salt and pepper. Okay, so that's one example. And what this tells us is, in this specific example, the best predictor tends to give us the map that that looks worse. And the best maps, which I believe are the SVM ones, tend to predict worse. Okay, that's one problem. If we're looking, so let me look at the same data set, but with a slightly more difficult task, which is face versus cat. And if we're looking on the mask of the ventral stream here with an SVM, we get an error of 24%. And what we see is that if we split the data in two, and we look at the first half, what the map looked like, and the second half, what the map looked like. Okay? So we run the SVM on the first half and on the second half. They're actually quite different. So where I'm trying to get at is that those maps are not very reliable. Now, if we do this in full brain, it gets horrible, right? The maps are really ugly, and the error goes very high up. So right now I'm just, putting problems, and I'll explain a bit why these are problems. And finally, to drive the message even further, if we look at very simple simulations, the nice thing with simulations is that we know the ground truth. So here I have a brain that is cubic, and on 4 ends it's got predictive regions. And I have smooth images of this brain, and I have a linear model, and I'm simulating my data. So then I'm going to run an SVM on it, and I'm going to look at what the brain maps it gets. So these are the brain maps, and I have numbers that qualify the quality of my prediction and of the quality of the recovery of brain maps. So bigger is better. So I can run sparse models. Sparse models predict better, but their recovery of brain maps is worse. And I can run univariate testing, and so if I run univariate testing, there's no prediction, but the recovery is much better. So I guess all this introduction was to drive home the point that, good brain maps do not mean good recovery. And this statement is hard to back, because then we have to define what good brain map is. Okay? But I guess I've introduced several set of examples based on simulations, based on looking at simple experiments with data set that tell us that if we have good prediction, we cannot always conclude that we have good brain maps. Okay? And now I'm going to try to get a bit into why this is happening. So the way you can think of it, if we're looking only at prediction, it's kind of looking at the shadow that is cast on a screen by our maps. We're not looking at our maps. We're looking at the effect they have in a very indirect way. Okay? So the problems we end up with is that not all informative features are needed to predict. I can take one feature, one voxel that has a very good signal to noise, and use only this one to predict. I'm not controlling at all what the ones that I have not taken are doing. And also the fact that I can put a lot of weight on uninformative features, and because they may average to 0, they may not harm prediction. Okay? So these are core problems. So now to get an idea of how we can address them, let me look a bit at how decoders, the ones that we all use here, work. And I'm going to focus on linear models. So in linear models, the idea is that I start from brain images, so observed images of brain activity, or some VBM images. And these are going to give me a design matrix. And then I'm going to try to learn a set of coefficients to predict well a target, right? To separate well for instance, stimuli. The nice thing is those coefficients are brain maps because they live in the same space. So in a linear model, basically, I can look at those coefficients and I can interpret them as a brain map. So that's my setting. The problem is I'm going to try to find brain maps to minimize this prediction error. And what you have to keep in mind is that this is an ill-posed problem in the sense that there are many different brain maps that will give the same prediction error, right? Because I have a huge number of options with regard to brain maps. I have, 50,000 or more or less voxels, and I have something like, let's say, 100 observations. So I can choose many different brain maps that will work as well. So how to choose one? Well, it is a somewhat arbitrary choice because it's not informed by the data, right? So each different approach will give me different outputs, and this is what we've seen. And there is nothing in the data that is telling us which one is to prefer. This is purely something that we as modelers are putting in. So if we look at support vector machines can be seen as exemplar-based classifiers. So if you think of your problem as a set of, two sets of points, I'm trying to discriminate between two conditions, and there are two sets of points, points with condition A and point with condition B, and each point is basically a brain image. Okay? What the SVM is doing is it tries to find a separating line, a separating hyperplane between those two sets of points, so between those images. And the way it's doing it is it builds this hyperplane by combining exemplars, by combining images, right? This is the way an SVM works. So when you think about this, then by construction, the hyperplane looks like the train images. Okay? If you want to be a mathy, you say it's because it works in the dual, it's because it's a kernel-based algorithm. Okay? So this can be good or bad, but it does mean that SVM maps will be distributed because none of these images, most often, if I'm putting brain activity images, are localized. So you need a huge amount of non-localized images to create a localized image. Okay? So this may be good or bad, depending on your point of view. So the framework we can look at to put a bit of math in this is the risk minimization framework that was introduced earlier. So the idea is that you're going to minimize an error term. And as I said before, this is ill-posed in the sense that many different brain maps are going to minimize the error term the same way. And so the way you're going to address this is to inject a prior to make this well-posed, and you can do this with a penalty. So that's a framework that's been introduced more than once, and it's also the framework that is behind the SVM. So if you use a specific form of penalty, known as the L1 penalty, then you can build sparse models. So one of them is the Lasso, and people have been excited about sparse model, at least I have, because the idea is that maybe they can select predictive voxels. Okay? So the way it works, to give you a quick intuition, is that you're minimizing an error term, which is the ellipse here, because it's a squared error term, and the L1 term is creating an energy that has corners, it has kinks, and because of the geometry of the minimizer, you're going to most often end up in those corners, and those corners are putting voxels to 0. So this is great, so the nice thing is that there's a lot of theory on this. And this theory tells us that when you have many correlated features, many correlated voxels, what these kind of estimators will do is that they will select a random subset of these features. There's a lot of theory on this, so there are proofs. And what this theory is telling us basically is that for neuroimaging, if we're working at the voxel level, this cannot work. And the reason being that two neighboring voxels are almost always heavily correlated. So what happens is that those estimators will select a random subset of neighboring voxels. This is well understood from theory. And in practice, it shows up. So there's actually a nice paper by Irina Risch, who's going to be presenting this afternoon, where she runs a lasso, and then she removes the voxels that were selected by the lasso, and then she looks at how well she can discriminate on the remaining voxels. And she goes on and on and on again like this, and she shows that basically you can discriminate really, really well by removing, even by removing the first models, okay? So this is telling us that we've missed a lot of predictive voxels. So sparse models by themselves cannot work to select all the predictive voxels. So a few more tricks that people use, that we use and that work well, is smoothing. We find that quite often you can smooth the data, including you can smooth it quite heavily, and you get smaller error rates. And the maps look smoother, which often is prettier. Now this is probably good, given that you predict better and that the maps look better, but you're really giving up on resolution when you're doing this. And another way that works really well is to do feature selection. Let's not do full brain. Maybe we might have a univariate feature selection, or maybe we might have a region of interest that we know from beforehand. And when you're doing this, so quite often your error goes down, and your maps, well, they're focalized on where you think it's interesting, but you're somewhat giving up on being multivariate. So this may be good or bad. So just to put a bit of big picture, it's important to realize that going from prediction to controlling the errors on brain map is, in general, intractable. If you don't have hypothesis on your data, given the sample sizes that we have, it's impossible to answer. And I work with people in statistics or machine learning, and they tell me, you know, you're just probably just saying bullshit given the amount of samples you have. And the only way we can get out of this problem is using suitable simplifying hypotheses, which when we think of it, we probably have, because we know something about what the brain maps should be looking like. At least I think we know. And I think what we know is that there is some form of spatial structure or contiguity, as in what's used in standard analysis with random field theory. And this is why, you know, smoothing in SVMs tends to work better. I think only a fraction of the brain, maybe a big one, but only a fraction of the brain is useful to predict, and that's why things like sparsity or feature selection work better. And we know that neighboring voxels are multicollinear. And we know that this tends to break multivariate estimators, and it's a core problem. You know, multicollinearity is a very hard problem. So this is where I'm going to introduce spatial regularization, which is basically built upon all this to try to answer these problems. I'm going to present two approaches that we've developed, and I'm not sure which one is the best, by the way. We're still working on it. And the first one is based on the idea that we're going to group together voxels with a similar response. So we're going to use clustering for this. We're going to use hierarchical clustering. And the reason being that, you know, if they look too similar, we're going to give up on trying to separate them. From the theory side, it's great because it gives us good conditions for sparse models. We can show that when we're doing this, we're moving into the recovery conditions for sparse models. So we have at least theoretical arguments to tell that this should work. So what we're going to do is we're going to run clustering to build something like a brain parcellation, and we're going to apply a sparse model on this. And hopefully recovery is going to work on this parcellation. And the idea behind this is that this problem of brain mapping in multivariate models is much easier on a parcellation. And it's the same idea that goes behind the MKL work that was presented by Jessica in the Filippone paper. Now, the problem is that the parcellation or the clustering is not always perfect, right? We're completely dependent on this. So what we're going to do is that we're going to perturb our data and rerun the clustering many, many times. Each time we're getting a slightly different parcellation. Each time we're going to run a sparse model on this, and we're going to, at the end of the day, we're going to aggregate the results, okay? So in a way, this is making us somewhat independent of the parcellation. And once again, we have theoretical arguments that this is probably good. And we've done, in the paper, we've done extensive simulations to look at when it works and when it doesn't work. And there are conditions when it doesn't work, of course. So for instance, if your regions are tiny, then it won't work because you're going to average the information in the parcellation. Okay? Makes sense. Now, to run this on data, this is a face versus house brain map. So if we run just sparse models, we find, a tiny number of voxels that are used to predict. Now, if we run the randomized clustered model, we find that we're really capturing much more, and we're really capturing regions that are in very different areas of the brain. I mean, I don't know if you can see, but up in the retrosplenial cortex, we're capturing a bit of retrosplenial cortex, which is known to be useful in identifying places, even though it's a fairly subtle effect. So because we don't believe one experiment, because we'd like to have conclusions that are wider than one data set, we've recently run this on a fairly large set of different tasks, including a VBM data set, not only fMRI. And what we've seen is that it almost always significantly increases prediction. It's hard for us to have strong conclusions on the brain maps. Now, on top of this, it's actually much faster than standard sparse models because we're working on a reduced feature set, and because we're aggregating data, aggregating results over bootstrapped versions of the data, the brain maps are actually much more stable. So this was pointed out by Jonas earlier, that when you have a lot of variance in your estimator, rerunning the estimator many, many times, and then averaging the results will give you more stable results. So we're getting better prediction and more stable maps. We cannot, guarantee you that those maps are the exact maps. We have no way of saying this, but at least we have hints. Okay, so another approach, in a very different kind of approach, is to craft a penalty that is designed to extract regions, because we think that regions are a good thing. And for this, we're going to still build on the idea of sparsity, and there are good theoretical reasons why sparsity may help us, even though we know that by itself it can't work. And we're going to add to this something to force regions. And the way we do this is we use something that's known as total variation, and the idea is that we're going to say that we want sparsity in the image domain, but we also want sparsity on the spatial gradient of the image. So we're going to put a specific a norm that imposes sparsity on the gradient. So this is known as total variation. This is somewhat related to GraphNet, which is some work by Logan Grosnick and Jonathan Taylor and co-workers, where basically they're imposing the image to be smooth, not sparse, the gradient to be smooth, not sparse. The reason why we like sparsity on gradient is that it tends to localize things a bit more. So if we run this, we find maps that are composed of smoothly varying regions that somewhat are reminiscent of what we find in standard analysis. And we can go even one step further and say we're going to combine this with sparsity. So now we have sparsity in the image domain and sparsity in the spatial gradients. Now this is something that we found works extremely well both on simulations and on actual fMRI experiments. This is something that has been historically fairly slow, and so for the last couple of years we've been investing a lot on better algorithms to solve this. So we're going to get this code out soon. We didn't want to get it out. This is work from a few years ago. The reason it's not out is that it was too slow. So we did not want to give code for people that is too slow. So we're talking now, let's say, 10 minutes on a standard fMRI experiment. So it's reasonably fast. So why do we think this may work? Well, so we've looked at the simulations, and this is the results from extensive simulations. So these results are actually very interesting beyond total variation plus L1 penalty. So what we're looking at here are things that look like RC curves, so they're precision recall curves, so they're very similar. So basically, a higher curve is better, and we're looking at whether we can recover yes or no active coefficients in simulations. We can only do this in simulations. And what this is telling us, these curves are really interesting because what you see in white is the standard f-test. So it's the univariate f-test. And what this is telling us is that the univariate f-test is doing extremely well. That, thresholding maps of multivariate models tends to work less well than thresholding an f-test to recover maps. Okay? So this is also telling us why feature selection using univariate feature screening works so well. Okay? And what we see here is that we've managed with TV and L1 to go a bit beyond the recovery, but it was somewhat of a struggle. And so we can see that we do better in terms of prediction error than other approaches, and this is somewhat comforting us that TVL1 actually works. But once again, prediction is much easier than recovering good maps. So to wrap up, because I think I'm running out of time, but before I wrap up, I'd like to touch a bit about software. I don't think that any recommendations that I might give you here, standing here, are useful if you can't run them. So we have this package that we call NiLearn that is in Python. You might like this or not, but we like this. It's very versatile, which means that you can play with those recommendations and see if you trust them or not. But it's fairly simple. We're working a lot on making it fast and efficient, and I think they're great docs and examples. So to conclude, I tried to hammer the point that standard decoders will not retrieve good maps, and this is actually not surprising if you understand what's going on. That we believe that spatial models are a good way to selecting predictive regions, and we have two approaches that are not yet in our software but will be there soon. We'll put them in when we think they're really ready for public consumption. This is useful because you can do reverse inference, for instance. And yes, I'd like to to close there. Thank you.
Specific question for Gary.
Are there any questions on this?
Specific questions for Gael? Yeah.
Hi, Moritz. How are you?
Okay, hi, Gael. So I suppose you already know what question I'm going to ask, so this is going to be fine.
I think I know the overall framework.
Yeah, good. Okay, so you said you want to investigate the neural support of a cognitive function.
Mm-hmm.
To me, this is tiptoeing a little bit around saying I want to understand how neural activity causes behavior.
Absolutely.
Or do I misunderstand that?
Absolutely.
Oh, good, thanks.
Absolutely. No, that's a great question. And I also mentioned something. I think it's important maybe to control both reverse and forward, which is you want something to be lit up reasonably well in a standard analysis and in a decoding analysis, which I think is something you're trying to push forward.
I think the total variation plus L1 essentially is the fuse lasso method, right?
No, I'd like to claim that no. First, I'd like to claim that fuse lasso was invented in the 2000s and total variation was invented in the 90s. And then second, there's a very big difference, is that the structure of the problem in fuse lasso. So fuse lasso is 1D. Total variation is n-dimensional.
I'm not arguing between the total variation and fuse. I'm arguing you said that the total variation and the L1. But fuse lasso essentially just the total variation plus L1.
No, there is a very big difference. The difference from going from 1D grid to 3D grid changes a lot of things, whether it's
that's a technical
It is not a technical problem. It changes completely the kind of results you can have on recovery, the kind of theory, and the kind of algorithms that you can run. It's a very vastly different problem. And the way you can think of it is that the size of your null space in the analysis sparsity framework is 1. You have a one-dimensional null space if you're doing a fused lasso, and it's almost the size of your initial space if you're doing total variation. So it's a widely different problem.
Actually, there's an R package can do that, and it can do the 2D and 3D space. You may want to try.
Well, on the program now, the program says now that we have a bit of time for more questions, general questions, and maybe discussion. So the idea is that if you have any issues, questions, demand for one of the speakers you heard this morning, this is really the moment, and there are no silly questions. So everyone is welcome to come up and pour their heart. We'll try to answer them. But yeah, and the other speakers should also contribute.
Can I?
Yeah, sure.
You've been talking about doing clustering to summarize voxels and reduce dimensionality. So what's your take about doing this in a supervised way? So using the response to cluster the voxels instead of just doing standard clustering.
Yeah, this is what is my take? My take is I don't really know how to do this. So we've done this a few years ago. Vincent Michel in 2011 had a supervised clustering paper for fMRI. The thing is, supervised clustering is a general problem. There are ways of doing this. I mean, we tackled it in a specific way. There are other ways by crafting specific penalties. I don't think it's a problem that's terribly well solved. I mean, the closest that gets to there would be a penalty that looks like TVL1 or structured sparsity.
I was thinking of something probably simpler, such as linear discriminant analysis. So you can project, I don't know, you can project parcels, maybe defined by some other technique, I don't know.
Well, so the LDA in the linear discriminant analysis, the LDA in the kind of dimensionalities that we have will not be runnable. You won't be able to run like a standard LDA, so you'll have to inject regularization in it. And so you're back to the original problem of how do you regularize this. And people have done very beautiful work injecting like structured regularizers in LDA. So this is actually like very beautiful work. And my take on it is it's great. My other take on it is, I mean, the reason why basically we have those two approaches, TVL1 and randomized clustering, is that there is maybe a factor of 1,000 in speed between the two. So we want to develop both because we think it's useful to have a very fast method and one that is maybe like more principled and controlled.
Okay, thank you.
And one reason why it might be fast is I believe in permutations.
I tried to see if I understood well or not something. As far as I could read Google and see in your slides, I thought kernels, what they do is try to get for each voxel how similar it is between two different classes of images.
For each map, not voxel, for each map. A kernel builds a distance.
But there is a matrix, and one point is one voxel, right?
No.
One point is one sample.
Okay.
One sample, it's one image. So if you have 100 subjects, your kernel will be 100 by 100. So it's sort of giving you, the intuition is it gives you the similarity between pair of images.
Okay, so I misunderstood. And my second kind of related question is, how is that different from the representational dissimilarity analysis like Rigo's Corte?
I have a hard time answering this question because I have a hard time knowing the math between RSA, because each time I pick an RSA package or I look at a paper, it varies. Now we've tried looking a bit at this, and actually Charles Cadieux, I think it's Charles Cadieux who has a really nice paper, by the way, drawing a link between RSA and kernels. So there's clearly a link there. Because that's exactly what they're looking at. They're looking at distances or similarities between observations. Now, formalizing it exactly requires formalizing exactly what we mean by RSA. But you can look at the paper by Charles Cadieux.
Cadieux,
yeah.
So in principle, it's related, but it's like different mathematics.
Yes. Yes.
Okay. And I have another question. Which is likely a very silly question.
Well, you're brave to ask it.
Yeah,
everybody's thanking you, actually.
So, if you were to try to use these kind of techniques to say, a la Huxley, or I also saw something like one area is involved, or a little bit what like your multiple kernel tool is using, saying this area is involved in the difference between these categories versus noun. Is there any way to say these two areas do together more than separately? Or is it like something that is out of reach? Is there any kind of model that you can compare, saying it's actually better to have the two regions together rather than...
Well, one thing I'd like to do, I think you need to, if I put on my statistician hat, I need to be more precise than this. I need to define two models that I'm comparing. I need to go basically from the general question that you're trying to ask, which is a legitimate one, to an actual specific question that I can answer with math. But one way
which would be like I don't know, Bayesian criteria or something like that. You can by information criteria to compare to models that you fit, or
one thing I would like to do, one way I would answer this question, and maybe it's not the optimal way, but I would compare an A-phase classifier, which is a classifier that basically assumes that features are dependent, and it's the predictive model version of a standard analysis. So it's basically mass univariate classifier. I would compare this with a multivariate classifier, and so I would do standard things explained by Jonas to compare prediction. And if my multivariate classifier predicts better than my naive-based classifier, well, there's probably some information in the joint distribution. So the joint information of those two features.
So you say the naive-based classifier would be like taking each beta value from an F-test or something?
Yeah, that's pretty much what it does.
Versus getting the whole pattern together and see if then you get better prediction.
Yes, that's pretty much it.
Okay.
Difficulty is the redundancy you have in the structures.
Yeah.
It's maybe those two areas are contributing, well, they have enough information on their own to do the classification. You could be using one region or the other or both. You would get pretty similar accurate prediction. So it doesn't mean that they are not, the two of them are not involved, but maybe in the task, in your neuroscientific question, but then each of them alone could be sufficient to do the prediction. So that's here the
But at the end of the day, most classifiers are linear, right? So at the end of the day, you have a like linear combination of
So the naive
ways.
base is not linear.
Okay.
Yeah.
Right.
It's a different framework.
Thank you.
I'm working on univariate modeling and power and the multiple testing problem. So you said in the beginning of your talk that univariate modeling, the problem is that it doesn't have power because we have to take into account the multiple testing problem. I agree with that, but isn't the fact that in decoding, the goal is to control the prediction error or to improve the prediction error and not the false positives? Doesn't your image in the end, like with RO seekers, exactly show that if you would put the same constraints on the machine learning techniques to false positives, that actually univariate modeling would perform better?
I think
in terms of power?
I think it's an excellent remark. Like basically every single thing you've said is completely correct. And if I can rephrase, indeed, they're not at all the same questions asked. And you can think of decoding as an omnibus test. And an omnibus test is by construction going to be more powerful than a family of tests on which you're going to control some family error, whether it's FDR or FWER. So you're absolutely completely correct. And the fact that at the end of the day, when we look at asking the test that we would like to ask, which is, okay, is this voxel yes or no related, then we find that univariate actually does pretty good because it's well designed for this. And the only reason why basically something like TVR1 can beat univariate is because it's using the fact that there is spatial structure, and so therefore we're more likely to find something activated in one spot if it's activated in the neighbor. But yeah, I mean, I completely agree with everything you said.
Okay, thank you.
I have a general question for all the morning speakers, particularly Anil. Mentioned this in his slide. You mentioned to use pattern recognition for multimodal integration of different types of images. Just wondering, like, how can that be done, or have any ideas or examples in going about doing that?
So you can, so where are you? I lost you. Oh, there you are. So you can do this using this multiple kernel learning framework, and people have done this with, for example, combining MR and PET for Alzheimer's disease classification. So it's something that people have sort of already done or already doing.
How about MR and diffusion?
MR and diffusion, I don't know precisely whether people have done it. I think people have.
I mean, the nature of the images is not that important. I mean, diffusion, you mean you turn your diffusion into an FA map or something. Then yeah, that's it.
I mean, so it's entirely plausible to do that. As to whether people have done it and found that it's helped them in their particular task, that's. I can't give you any specific examples right now, but there's no reason why you can't do that and why it shouldn't, in theory, help you. As long as, I guess, the information is in some sense complementary. Yeah.
The simplest people we're using is just stacking up the data. I mean, you just put all the voxels together and you just have twice the amount of data. But then what is more interesting is finding the contribution of each image. That was the multi-kernel idea, was you learn what is the balance, the contribution of each modality, and then at the same time you learn the patterns, or you do the training with
So maybe I can have some since it's an educational course, I can have a super educational answer. So you can think of this, so this is an old school problem called the data fusion problem that comes from Radar, from million tree applications. And you can think of it as really, you have several ways, several levels in the information processing chain where you can do this fusion, this multimodality, right? The very basic level is the data level, which is what Chris was mentioning, and one way to do this is really just making a big vector out of everything, okay? And that's, in theory, that's where you have the most power, because you can see all the data, you can exploit the complementarity, but in practice it's difficult because of the high dimensionality. The second level, where you can do things, is features. So then you can think of reducing your data in some sense. One of the classical things you could do is a PCA, then have smaller dimensional space. You could do it like this. And another very abstract level that people don't necessarily use very much these days is really the score level or decision level fusion, where you would train a classifier on each modality, and then you would model the joint score space. So instead of the function values I was showing before, you would have several function values. And in this, you could do a bunch of things. You could have like a mean rule that works very well in general, or you could train, like this is called a stacked architecture. You could just stack things together and learn a second level classifier if you want. So this is basically, as you move up the layer, you lose a bit of power theoretically, but it becomes more easy. And then the top level you could do is just decision fusion, where you could do, each classifier would vote, class 1, class 2, and then do a majority vote. But and of course you have MKL. I think the most interesting thing is really like if you go lower level, that's where, or intermediate, that's probably where you're going to get the most power.
Actually, might be
Okay. Well, thank you. This is another really basic question. I know some of your slides are really wonderful. Just wondering, are they available somewhere online?
Yeah. Whose slides are wonderful?
All the colorful ones.
Everyone's slides.
I know I have Jessica's.
I don't know why only some of the talks are available at the moment, but I promise we'll get all the slides up there sooner than later. I don't know exactly. I guess everyone was late to send in their slides.
Yeah, apologize. We didn't share
weeks in advance is yeah. I don't know. This is more of a technical issue here.
That's okay.
But I mean, I sent mine Wednesday, and they are there. I know that people send them before, and they are not there. So I'm not sure.
My slides are on SlideShare. If you find my SlideShare account, you'll find them. I upload them just before. On SlideShare?
SlideShare. Okay. Excellent. Thank you very much.
Other questions? Or everyone is hungry?
Hello. I've got a question. So if I want to look at, I've just got an fMRI experiment looking at some memory networks. So if I want to do decoding on several anatomically defined ROIs, would it be suitable to use this multiple kernel learning? So one kernel for each ROI?
Exactly.
Yeah? Okay. Cool. That was easy. Thank you.
Also, just the question of program. Irina Rish will not be around. I think she wrote her life, and she wasn't able to travel. So I think George will be covering her talk, and Moritz will extend his presentation on MEG classification and brain computer interface to some more causality issues. Just to let you know that the program had to be adjusted slightly. I hope for the best.
Just a very basic question. I'm just beginning to work with MPPA, and I know that there is not a specific answer to this, but is there, in your experience, what is the best design to use for an MPPA experiment?
What sort of experiment are you talking about?
Let's say that you have some categories like faces, capsules, cats.
fMRI.
Yeah, in fMRI.
Block designs. That's
block. So I mean, whether event or block. Like one thing, if you ask an engineer this, then my answer would be I want 1 million blocks, and I want like 10 seconds between each blocks to avoid HRFs, right? So we're going to always push for more data and to have a bit more spacing. That's a general thing. And then there's other tricks you can use, but that's just like my one bit that you should be. I mean, it's a very good idea if you think in advance that you're going to do pattern recognition analysis. It's really, really good to come and talk to people that do this kind of analysis, just because we have slightly different constraints about the data. But that's it. I mean, that's probably behind the scenes.
Yeah, I mean, my point of view on this, because we run into this quite often in the lab, is if of course you've got probably constraints on the cognitive design. There's you can't, depending on the question you want to ask, you need to build your experiment around this. But usually, event related, you certainly do not want long blocks, because long blocks will mean that there'll be less noise in each block, but you'll have much less samples to get to your classifier, right? So most often, you want event related, and you want just enough gap between the events to basically not have overlapping HRs. Yeah, but the goal, and the reason I'm saying this, I completely agree with Jonas that the biggest take-home message is we want as many repetitions as possible, and that's why I'm pushing towards events rather than blocks, because events will give us more repetitions.
Yeah, and we usually, basically, like the the results are kind of like the same. We looked at it a little bit. If you take the block and average, or if you look at events as well, if you do what you can do is do a GLM before you enter the multivariate analysis and just use the beta maps so that you kind of take out the convolution problem for short events.
It's a way of getting one image per event. So the idea is by putting the GLM, you're able to remove things that you don't want, like the HR. So you're estimating the amplitude of the response to each event specifically. So instead of modeling like your 25 events in one column, you model that as 25 columns. You would get 25 estimates of the activation for each of your presentation. That would be one way. And there, yeah, I said block because it does increase your signal to noise, but a block and an event are technically very similar. An event is a very short block, in a way.
One last thing maybe about betas, and I think that's also interesting because if you treat a set of betas and use that, then you have some guarantees about orthogonality and more independence between the betas because they take out some part somewhat, but you're kind of taking care of it, you're kind of partially out with respect to the rest. It's not entirely so simple, but it means that you're maybe a bit closer to meeting the independence assumptions that you have.
And that technique is often known as beta series regression. If you want to look it up, it's often known as beta series regression. Okay?
Yeah. Well, I'm like wanting to jump in here because I wouldn't be nearly so dismissive of saying that you absolutely must have as many examples of each class as you must. I've sometimes had extremely good luck with, temporally compressing down to one example per person per run, one example per person even. It totally depends on what you're doing. If you're going to be doing a lot of really hardcore, let's see how many models we can fit, let's see how much we can really push our accuracy, then yes, you need more examples. But if you have a very strong hypothesis going in that you know what you're testing for, and you know I'm just going to use a linear SVM, C = 1, I'm going to use these regions, I'm not going to do a lot of fitting, sometimes it can really boost and you can get extremely good performance if you're going to the option of fewer examples, but each one less noisy, particularly for multiple subjects, I would say. So I just had to fight against your guys' assumptions a little bit there, or assertion.
And just another very basic question. I'm just beginning to work with it, so I'm using PyMVPA, and I'm using that suite, but I can see that the examples that you can see there are examples for experiments that are categorical. I mean, you have faces, houses, cats, etc. But what about if you have a stimulus like orientation bars that is not actually categorical, it's continuous? So what kind does PyMVPA allows me to work with that kind of data, or is there another suite that I can use to work with it?
I don't know about PyMVPA, and hopefully there is some PyMVPA people there. But I mean, your example about the rotation is a specifically difficult one because it's continuous, but continuous going around. Not it's not like age, which is continuous in another way. So rotation is especially difficult, and I would be surprised that PyMVPA does this out of the box. It's like it's the problem. But if you have continuous variables like age, for instance, then the kind of problem is known as a regression problem, and machine learning toolkits usually have tools to tackle regression problems. I don't know specifically about MVPA, but I would expect them.
Sorry, which one? Okay.
I can't say about PyMVPA because I don't use it, but in general, machine learning toolkits tend to have, so they're called regression tools, and they tend to have tools for this.
Well, and for PyMVPA in particular, the mailing list is really, really useful for that, and I know for a fact that Yaroslav Helchenko and a lot of the main PyMVPA developers are here. He's supposed to be outside the door, actually, in about 5 minutes. So if you keep your eyes open, you should be able to sit down and really talk to them about how to do this in a high MVPA savvy sort of way.
Thank you.
Yeah, so regression is there in most toolboxes. The difficulty with your angle is it's because when you reach 360 degrees, you're back to the beginning, and there that would require some specific ad hoc. It's a regression problem, but because the end of the circle is the beginning, the idea of there that should be that constraint should be
yes, really taking that into account. Yeah.
In the model. No, if you just modeling like between 0 and 180, that would be sort of the same derivative.
So you can, I mean, one way we've done this, because to do this in a clean way is a lot of work. One way we've done this is predicting the x and the y. So basically, you can see the angle as a point in a circle, and you're predicting the x and the y, because then you don't have that many constraints on the prediction. You're decoupling the constraint.
Thank you.
I wanted to ask about the region of interest. I don't exaggerate, but about the fact there was in one slide the fact that we need, if we want to use region of interest for feature selection, to use an independent data set. But I was wondering if, in the case, say, where you have an event-related design with faces and places, if that would be acceptable to actually take as a region of interest an independent contrast, which would be any visual stimulus activation in that data set, which is an independent comparison, like orthogonal to faces versus places, and then use that. I don't know if it's reasonable or not, and then use that as your region of interest to do the classification comparison.
So the constraints of independence is that when you do your cross-validation to measure model error, you want your trained test to be independent, your test set to be independent from everything you've seen during training, as in statistically independent.
Sure.
So,
but that's a different thing. It's just for region of interest selection before any.
Well, but that region of interest, if you look at your data, if that region of interest is not statistically independent from your data, then your training is not statistically independent. So basically, if you are sufficiently well separated in time, you can assume statistical independence. It's not completely true, but it will work. But if you have interleaved conditions, and so you've done face, house, and cats, and in this order: face, house, cat, face, house, cat, face, house, cat.
Yeah, except if we take the beta images, like we were saying.
Yeah, but so the orthogonality. So when you're running the beta images, you're like orthogonalizing your design, but you know it's.
So the best is just to take something from the literature then.
This
or from another experiment.
You might want to, typically, I mean, when you're doing experiments, typically it may be useful to have a localizer contrast in the beginning. And because it's in the beginning, it's not interleaved with your cognitive experiment, then you can assume it's independent.
Okay, thank you.
Yeah, well, you just do nested cross-validation. That works as well. We did it actually in the +1 paper. Just look at all what was active for the 3 conditions, and then get into the modeling part where you distinguish between them, but it's still feature selection.
Can I ask another very basic question? So I got the point that you really have to separate your training data from your test data. So how large is the sample? I know it's really basic. You're saying that your parameters have to be smaller than the design, right? But it's like, how large is the sample? Let's say I have a clinical group and a control group. Like if I only have like 30 subjects in each group, is that too small?
It's not too small.
So I mean, so that really depends on. It's always dependent on the effect size. So basically, if you can do statistically, if you can do super well with your classification, let's say you have like left hemisphere, like less left hemispherectomy. Okay, good. But you don't have part of the brain versus rest. Probably you can classify super well, like 90%. And then you'll be way above chance, right? But like you can't really say, I mean, unless you know from the literature, you can't really say in advance how easy it's going to be. But to be safe, basically to be safe, if the task is easy, then you can do it with fewer samples, just like in classical statistical testing, right? Like if your effect size is huge, you don't need as many samples.
So how many training samples would I need? I mean, is there any guideline?
So if you have 30 and 30, and say you've got much subjects, healthy controls are matched, or the patients are matched with the healthy control, then what you could do is subject throughout.
Yeah, so no, that's I mean, there are two different questions. One is how many subjects should I have in my total thing, and the other question is how should I split my data?
Yeah, that's right.
And I'm amazed to see that the neuroimaging community does so much leave one subject out, or leave one out. So basically, there's no general result, no general proof for every classifier, every problem, but there are a set of specific proofs for specific classifiers that shows you that if your test set is too small, so typically if you're doing leave one subject out, you're completely biasing positively your results, and that you have a very bad estimate of cross-validation performance. So typically in machine learning, what's recommended is you leave out 20% of your data. That's the typical recommendation. And if you have a huge amount of data, you may want to leave out more. And I'd really like to get this message out. If you go to a machine learning conference, basically everybody does this. If you go to a neuroimaging conference, everybody does leave one subject out. It's not a good way of measuring error.
But I guess it's also what the question is, though. Like, if you want to be good at modeling your data set, then you want to use as many training samples as you want for training. Because and if you really want to report a generalization error, then you want a good test set. But if you want to look at the weight maps or which one, we know.
If you want to look at the weight map, you refit on everybody or your average weight map to do something. But if you want to report an error, you should be doing this using one subject out.
And that's why I also use speed permutation, because that accounts for the fact that they also are not totally independent. And
it does, but what you have to keep in mind is that when your test set is tiny, your error on the error is really bad.
So you get an accuracy estimate, but that accuracy estimate, the number you get is not the most reliable number. Still, if you do things properly, you can get, if that's above chance level. But then that doesn't really mean that if you get new data, you will have a good prediction.
So just to go back to what you're saying, how many subjects I need. So this, what we discussed now, is like how many subjects you need to have good confidence intervals on your prediction and estimate of the generalizability. But it doesn't tell you how many subjects you need to learn well for your particular program, and I think you absolutely cannot. It's very problem independent.
One tool, though, that you can use is something that is known as a learning curve, is you take your whole data set, and then you randomly subsample it. So if you have 900 subjects, you randomly take 800, and you do cross-validation, you look at the performance. Then you randomly take less and less and less. And so that's a learning curve. It shows how well your performance is doing depending on the number of subjects. And basically, so you plot this as the number of subjects, and you can see whether you're starting to level out, in which case there is no point acquiring more subjects, or if you're still going up. And so I can tell you that recently for resting state classification of autism, we were looking at 900 subjects. It was still going up at 900. What is this telling you? It's telling you that classifying autism with resting state is a very hard problem, which we know.
Gael, wouldn't you agree, though, that in most neuroimaging studies we're super far from the asymptote? Like we're kind of there, the curve, and
so basically more data is always,
so
almost always better.
For a beginner, I mean, like, is there a point where I could say, oh, I shouldn't even try this, I don't have enough?
I've had people walk in my office with 8 samples from each class. I am not comfortable with this at all, I can tell you.
For your thing, 30.
I think officially 30 of each class, give it a try.
And then 20% for training?
Yeah.
For each class?
Yeah.
Well, I think it's fine to break on for lunch. And it's supposed to be back at 1 p.m. You want to attend the rest of the course? Yeah.